So last time we proved Castelnuovo's theorem, and the upshot of that was that if X is a smooth projective surface, then we know that there exists a sequence of blowdown morphisms down to some smooth projective XM, which is a minimal surface, so it has no -1 curves. And now our goal from here is to classify the possibilities for this minimal surface. So today we're going to focus on the case where the canonical bundle of XM is not Neff. So let me write down the final theorem we're going to sketch the proof of today, which is that if KXM is not Neff, then XM has one of the following two forms. Either XM is a P1 bundle over a curve, or XM is Fano, meaning minus KXM is ample. And actually, if you work a little harder and use some surface geometry and some statements about P1 bundles over curves over algebraically closed fields, you can get more. You can actually see that, in fact, in this first case, XM is actually a ruled surface. So it's actually the projectivization of a vector bundle on C. And in the second case, it turns out that any minimal surface that's also Fano over an algebraic or over the complex numbers is actually just P2. But we're going to focus on just proving the weaker statements that you get either a P1 bundle or a Fano surface. And note in particular in each of these cases, or maybe I'll leave this as an exercise. In this case, we actually have that no powers of the canonical bundle have sections, which implies that we're in the Kodaira dimension minus infinity case. Okay. So that's what we're going to do today, or at least we're going to sketch this today using some theorems that we'll prove later in the class. Okay, any questions about this statement? Okay, and then from here, once we have this statement, then what we're going to do is consider the other case where the canonical bundle is not an F, and then we're going to see that in that case, the canonical does have sections, and so we have to be non-negative Kodaira dimension, and so this will give us a classification by Kodaira dimensions. But for today, all we'll know is that if we end up with a minimal surface whose canonical bundle is not an F, then we're Kodaira dimension minus infinity. The converse will be next time. Okay, so our strategy, or how are we going to use that the canonical is not an F? Well, that means that we have some curves whose intersection with the canonical is negative. So our strategy will be to understand what are these curves and use them to construct a morphism, a linear series that will exhibit XM as either a P1 bundle or as a Fano variety. Okay, so I want to start then by just seeing some examples and counterexamples about the behavior of this cone of curves before we actually prove something about it. So if we recall, the definition of this cone of curves, NE of x, was the set of linear combinations of effective curves where these AIs are positive real numbers. And by definition, this sits inside of what we can call n lower 1x, and maybe with an r, though sometimes I'll drop the r, which is numerical equivalence classes of curves with real coefficients. But because we're on a surface, we'll make use of the fact that this is the same as n1 of x sub r, numerical equivalence classes of divisors with real coefficients. So that's one of the things that becomes more complicated in higher dimensions. And then we define this closure. And this closure means in the real Euclidean topology on this real vector space. And this vector space has a pairing. So given my intersection product, and this is one of the places we'll use that n lower 1 and n upper 1 are the same. So if we have some vector space with a pairing, and suppose that K inside of V is some convex cone, we can define its dual, which will also be some cone inside of V by the formula that this K star is the X in V, whose pairing with Y is always non-negative for all Y in K. Okay, so that's the definition of the dual cone, and then our first fact, which is basically a reinterpretation of the definition of being Neff, is that the cone of Neff divisors is exactly the dual cone of any X bar. That's basically a restatement of the definition of Neff, that when you intersect with an effective curve, then you get something non-negative. And so, of course, here, so for us, the intersection product, for us, the inner product will be the intersection product. Okay, and then we also can talk about the ample cone, which is the convex cone of all ample divisors, so non-negative linear combinations of ample divisors. And we had Kleiman's criterion. So Kleiman's criterion told us that this ample cone was the same as the X in N1, such that X paired with Y is strictly positive for all Y in NEX. So it's a restatement of Kleiman's criterion for ampleness. And from here, we get, as a corollary of Kleiman's criterion, we get that this ample cone is actually the interior of the Neff cone. So I won't write out the details there. I'll leave that as an exercise, but It's essentially a corollary of Kleiman's criterion plus using the fact that being ample is an open condition. So whatever this ample cone is, it has to be open. It's contained inside the Neff cone. The closures are the same, and you can check that. That implies this interior effect. Okay, and then just a remark. In higher dimensions, when we do this, now we'll have to generalize a bit because our intersection pairing will be a pairing between n1 of x and n lower 1 of x. And these vector spaces will really be different spaces, and so we have to write down the same definition for an external dual, where now the dual of a cone in V will be a cone in a different vector space, but then these statements are still true in higher dimensions as long as you know which cone you're inside. I want to give some examples and counterexamples to basically justify why we need to work with the closure and to show how complicated this closure can actually be. So the first example is the surface E cross E, where let's say E is an elliptic curve. And let's assume that the endomorphisms of E as an abelian variety are the integers. So this is an elliptic curve without complex multiplication. So here, these endomorphisms are all just multiplication in the group structure of the elliptic curve, multiplication by some number n. Okay, so the first thing we want to do is write down n1 of x. And to do that, we can use the following formula for the Picard of a product of curves. So if I take two curves C1 and C2, it turns out that the Picard of this product is pic C1 times pic C2 times HOMs as abelian varieties between the Jacobian of C1 and the Jacobian of C2. So that's a general fact about Picard of products. You can find it in some reference on abelian varieties. So in our case then, pic X will be essentially E cross Z for the first copy of E, and then another E cross Z for the second copy, since E is its own Jacobian and then Z is the degree. And then here we'll have a HOM between the Jacobians, but since these are elliptic curves, this will just be HOMs from E to itself. So we'll get this copy of the endomorphisms, which we assumed was Z. So if we mod out by numerical equivalence, everything inside of E is numerically equivalent because it's some connected family. And so when we mod out by numerical equivalence, we get 3 copies of the integers. And so if we tensor with R, so I'm trying to keep to the convention where if I don't put any subscript on n1 of x, then I mean R. Then this is a 3-dimensional vector space. And we can write it as the span of the following 3 divisors. So let me just draw a picture. Here's E cross E. How do we identify Picard of our curves inside of this product? Well, they're by pullback. So something in Picard of C1 means I'm pulling back from my first curve. So these will be divisors that are vertical. And then in Picard of C2, I'm pulling back from the second copy. So these will be divisors that are horizontal. And then finally, what's the divisor corresponding to an endomorphism? Well, the endomorphisms are generated by the identity. That was our assumption on E. And the identity corresponds to the diagonal. So these are the 3 divisors that generate these 3 pieces. And of course, any 2 fibers are numerically equivalent. So these generate N1, and we'll call them F1, F2, and delta. So N1x will be the real span of these three, F1, F2, and delta. And now from this picture, we can try to compute the intersection pairings. So F1 squared, that's 0 because we can move F1 to be the fiber over a different point and it's disjoint. Similarly, F2 squared is 0. And then delta squared, well, we're looking at the self-intersection of the diagonal inside of a product. The self-intersection of a curve, one of the definitions of the intersection product is that this should be the degree of the normal bundle of the diagonal inside of X. So here delta is the actual embedding of E into E cross E by the diagonal map. And if you remember, one of the definitions of differentials on a scheme tells us that the co-normal bundle to the diagonal is the sheaf of differentials. So the normal bundle to the diagonal is the tangent sheaf of E. But E is an elliptic curve, so its tangent sheaf is trivial. And so delta squared is also 0. Then just from looking at this picture, we can also compute the intersection of these vertical, horizontal, and diagonal with each other. And it's always 1, as you can just read from the picture. So okay, so F1, F2 is equal to F1 delta is equal to F2 delta is just 1. And so if we wanted to write down the intersection matrix for this, we get the matrix 0, 0, 0, 1, 1, 1, 1, 1, 1. So this is our Gram matrix for our inner product. Okay, so now we've completely computed our N1 with its intersection product. If we identify things in this basis, then we can identify a vector in N1x with a triple where this is xf1 plus yf2 plus z delta. And so if we use this intersection pairing, we can compute what's v squared. And in particular, v squared will be 2xy plus 2xz plus 2yz. And now we're ready to compute the cone of curves here. So here's a proposition. The cone of curves of X is the following cone. Well, first, we know by Kleiman's criterion, if we have any ample divisor, it better be positive on curves. So fix some ample. It doesn't matter which one we pick. Then whatever this cone is, it better be contained in the half plane given by a dot v is greater than 0. And in this case, it's going to be the intersection of this half plane with the cone of v such that v squared is greater than or equal to 0. So let me draw a picture. So we have this, we have this inner product, so we know what v squared is. We can write it down in terms of x, y, and z. And if you do that, you get this kind of circular cone. So this cone is the cone of vectors whose square is greater than or equal to 0. And then A defines for us some hyperplane. This is A equals 0. And so intersecting with A greater than 0 is like saying we're picking out half of this kind of two-sided circular cone. And so we get that our N of x will be this thing over here. Okay, but note that this thing is round, so the kind of slopes along the boundary can be irrational. So this gives us our first example where the closure is not the same as just the cone of effective curves. It's kind of the first example where we really need to take this closure. And you can see that because any effective curve will be an actual integral divisor. And so the slope of the lines spanned by effective curves have to be rational. And so what is any of x inside of any bar of x? It's going to be the convex hull of all rational, of all rays with rational slopes inside of any bar. But that won't be everything because we have these irrational ones. But of course, when you take the closure, you can approximate any irrational slope by rational ones, and so we get the full round cone. Okay, so the first thing we'll see, or the first claim, is that we have the following inclusions. If we look at the ample cone, well, any ample divisor is effective because some large enough multiple has enough sections to embed into projective space. So we know the ample cone is inside of any x. But in this particular example, I actually claim that any x is inside of the Neff cone. So this is the first claim. So that will often not be true, but here's the proof of the claim. So if we have two effective curves, D and C, inside of Rx, well, we have this action by E cross E, because E cross E is actually a group. And this action is transitive. So we have a transitive group action. So in particular, if we take some tau in here, we can act on our D so that now we move our D so it intersects our C properly, meaning that that D and C will intersect in finitely many points, maybe with some multiplicity. But then that tells us that the intersection of D with C is equal to the intersection of tau D with C, because E cross E is connected, so any translates are all going to be numerically equivalent. And because the intersection is finite, then this is the same as the sum over intersection points of some multiplicity, which is non-negative. And so this whole thing is non-negative. So this tells us that the intersection of any two effective divisors is non-negative. So any effective divisor has to be Neff. Okay, so that was the first claim. And then let me give some notation here. Let's call this cone our candidate cone. Let's call it K. Well, any Neff divisor, by definition, has to satisfy that v squared is greater than or equal to 0. So we also have the final inclusion that the Neff cone is also contained in K. Actually, let me give one more containment. So that's true, but we know a little more. So we know that the ample cone is so we know that if we take the closure of the ample cone, we get the Neff cone. And now that we've sandwiched the effective cone between the ample and the Neff, then we know the closure of all of these things has to be the same. So this tells us furthermore that the Neff cone then has to be any bar. And then, which also has to be contained in K. Okay, so that was the first part, is we have this sequence of inclusions that implies that Neff is equal to the closure of effective and that it's contained inside of K by definition of being Neff. So next, we want to give an inclusion the other way to get this equality. So on the other hand, we're going to show that if we have some V that's inside of K interior, and let's assume that it also has rational slope, then we're going to show So our claim is that this implies that V is effective. And then because K is the closure of this intersection of the interior with rational points, then we'll get that K is contained inside of any bar. Okay, so to prove this, we're going to use Riemann-Roch. So here we have to pick something with rational slope because we want a multiple to actually be an integral divisor and to actually correspond to a line bundle. So on our assumptions, we know that there exists some m, so that mv, and here m is greater than 0, there exists some m, so that mv is actually the class of some integral divisor. And now we can use Riemann-Roch to compute the space of sections, because essentially V being effective is saying that this D has some sections for some large enough M. So if we compute, Riemann-Roch tells us that the Euler characteristic of OX twisted by D is the same as 1/2 D minus KX plus the Euler characteristic of OX. So we need to know what are Kx and what's chi of Ox. So first fact, well, X is E cross E, and differentials on some product, well, they're the pullback of differentials from each piece tensored together, but on an elliptic curve, direct sum, but on an elliptic curve, the differentials are trivial, so this is actually 2 copies of O. More generally, anytime you have an abelian variety, Kähler differentials are trivial. And so that also tells us that the canonical, which is the divisor corresponding to the top wedge of this bundle, is also trivial. And that lets us compute this Euler characteristic. So let's write it down. Chi of OX, this should be H0 of OX minus H1 of OX plus H2 of OX. And this is 1. This H1, here we can use some Hodge theory. To get that this is the same as H0 of omega, but that's H0 of a rank 2 trivial bundle, so that's 2. And then H2 of O, here we can use Serre duality because the canonical is trivial. This is the same as H0 of O, which is 1. So that tells us that the Euler characteristic is just 0, 1 minus 2 plus 1. So this cancels out in this formula. This K is 0, so the intersection of D and K is also 0, so this cancels out. So we get that the Euler characteristic, so here, let's write down, that's Riemann-Roch. So we get that the Euler characteristic of OX twisted by D is 1/2 D squared, but D is M times our class V, so this is the same as V squared over 2M squared. For on the interior of K, then we have V squared is greater than 0. And M is greater than 0 as well, so this is greater than 0 because we're on the interior of K. Okay, but that tells us that if we write down the definition of this Euler characteristic, this is H0 OX of D minus H1 OX of D plus H2 OX of D. So this tells us that either H0 OX of D is positive, in which case we have a section. So then if we're in case one, we're done, because that's what we wanted to prove. We wanted to show that this V is effective, because that would tell us the reverse inclusion that K is contained in any bar. Or that happens if this first term is 0, but we could also have that this H2 is 0. I'm sorry, is greater than 0. So, or H2 OXD is greater than 0. But if we use Serre duality here, this is the same as H0 of omega x minus d, but omega is trivial, so this is H0 of OX minus d. So in this case, this would imply that minus d is effective. But that would imply that if we look at our ample, then minus d dot our ample is greater than 0, but minus d dot our ample is minus of d dot a. And that's a contradiction, because our assumption was that d was in this cone, which was the intersection of where a is greater than 0, and where v squared is greater than or equal to 0. So on the one hand, if H2 is non-zero, then minus d dot a is greater than 0. But on the other hand, by assumption, d dot a is greater than 0, so this is a contradiction. So 2 can't happen. Yeah. And so that's kind of, this last part is why we have these two pieces in this cone, and one piece is where H0 is non-zero, and some of the other pieces where H2 is non-zero. And so we're using our ample to pick out the correct half. Okay, so 2 can't happen. So that implies that we have to be in case 1, where D equals MV is effective. So K, which is the closure of this interior intersect rational points, is contained in the closure of the effective cone. And so we're done. Now we have the reverse inclusion. Okay, so that's our first example that this effective cone can be complicated. It shows that we need to take the closure. It's not already closed, and it can be round and contain these irrational slopes. Okay, but now you might say, well, that's not so bad. We could just work with this convex hull of all the lines with rational slope. Why do we need to take the closure? So let's give another example to show that we actually need to take the closure if we want things like Kleinman's criterion. And for this, we're going to look at some ruled surfaces. So let's say that X is the total space of some rank 2 vector bundle E, or is the projectivization of some rank 2 vector bundle E. And let's assume that E has even degree. Well, so if we have an E with even degree, we can replace it. Let's say even degree 2K. Then we can replace it with E tensor L, where L is some line bundle with degree minus K. And then the degree of E tensor L will be 0. But on the other hand, if you tensor a vector bundle with a line bundle, it doesn't change the projectivization, because when you're projectivizing, everything's up to scaling, and tensoring by a line bundle is just scaling inside the fibers. So P of E tensor L is the same as P of E. So without loss of generality, we can just assume that E has degree 0. Okay. So now we want to compute the cone of curves of this surface. So let's start with the Picard group. So we have the projective bundle formula. I won't write down the full projective bundle formula. You can find it in some text on intersection theory, for example. But here's what it says for PIC. In this example, the Picard group of X is the same as pullbacks of line bundles on C, direct sum Z O of 1, where this O of 1 is the universal quotient bundle, or the universal O of 1 on this projective bundle. So projective space is the space of quotients of some vector space. So this projective bundle is the space of line bundle quotients of E, and this O of 1 is this universal one. But you can think of it as the line bundle on X, whose fiber is the universal line, since points on X correspond to a line and a line quotient of the fiber of E. Okay, so that's the first fact, is that this PIC of X is this direct sum. And let's give a name for the numerical equivalence class of O of 1. Let's call it Xi. The projective bundle formula will also tell us that Xi squared plus the first Chern class of E times Xi plus the second Chern class of E will be 0. So this gives us the relation for the intersection pairing on this Picard. But we're on a curve, so the second Chern class is just 0. And also C1 of E, the first Chern class, well, that's the determinant of E as a line bundle, but as just a numerical class, it's the degree of E. And here we're assuming degree E is 0, so this also vanishes. And so our relation is that Xi squared is 0. So that gives us the first piece of our intersection pairing. If we go to numerical equivalence, then this will be the span. So pi upper star of line bundles, so we're pulling back from the curve. So if we're looking at numerical equivalence, any line bundle is just numerically equivalent to degree times a fiber, basically, because we're pulling back, and it doesn't matter which point you pull back if you just care about numerical equivalence. So that piece under numerical equivalence just becomes one-dimensional, spanned by some fiber, and then we have this other piece spanned by Xi. So our numerical equivalence classes are fiber and relative O of 1. So we also know now that F squared is 0. So if we intersect two different pullbacks, we can move them so that their pullbacks are that are of disjoint collections of fibers, and so their intersection is 0. And Xi dot F, well, Xi is this relative O of 1. So by definition, that means that on each fiber, it's O of 1 for P1. So we have this P1 bundle. And so when we intersect it with a fiber, we have to get 1. Because O of 1 has degree 1 on P1. Okay, so the intersection matrix here is 0, 1, 1, 0. Now we want to compute the effective cone. Let's recall that was our goal. So let's see what effective divisors look like. So let's say E in X is some effective integral divisor. Well, then by definition, E has to be the vanishing of some section of some line bundle. But now we know what line bundles look like by this projective bundle formula. Line bundles look like pullbacks from the curve, tensor multiples of O of 1. So whatever E is, it has to be the vanishing of some line bundle of the form OX of M tensored with some pullback from the curve. And now we can compute this. So first, if E is in this vanishing, then what's its class? Its class has to be of the form M psi plus degree of L fiber. That's the numerical class of E, because just from the definition of the F class and the psi class on our X. And so in particular, we know that let me not say that. So that's the class, and now let's compute what are these spacer sections. So here we're going to use the projection formula. So H0 of OX of M tensor some pullback by projection formula will be the same as H0 now downstairs on C. This part is just a definition of push forward. So H0 on C of the push forward of OX of M tensor pi upper star L. And now we use projection formula to get that this is the same as the push forward of OX of M tensor L. Now that's those are some coherent sheaves on C. And now this push forward, if you unravel the definition of the proj that you're taking to produce this projective bundle, then this push forward of OX of M essentially by definition is the mth symmetric product of our bundle E. And so we know what sections are then. Sections of OX M tensor pi upper star L are the same as sections of sim M of E tensor L downstairs on the curve. So every effective divisor corresponds to some section of a line bundle like this. And then so note here, we also have, once we know these intersection products, and once we know this description for effectives, never mind, I need one more fact first. Okay, so now we want to pick our E to have some nice properties to be able to compute the effective divisors here. So now that we know effective divisors are the same as sections of sim M of E tensor some line bundle L, and we also know that this L has degree the same as the coefficient here in the numerical class of E, you see that the numerical cone, the effective cone of these surfaces depends on the particular choice of vector bundle E, and specifically depends on what sections its symmetric powers have. So here's a fact about bundles on, say, higher genus curves. So if G of C is greater than or equal to 2, then there exists what are called stable bundles. And the important property of these stable bundles, I won't give the definition, but the important property they have is that for these stable bundles, if this space of sections is non-zero, then that implies that the degree of L is positive. So this is the important fact, that if we had started with E a stable bundle, then the only way we can have sections is if this L has positive degree, strictly positive. And so the way you produce these bundles is by Narasimhan-Seshadri correspondence. So there's some correspondence that between stable bundles and represent certain representations of the fundamental group of your surface. So here we're really using that we're over C, and then that lets you produce stable bundles. And then from the definition of stable bundles, you get this this property that if this tensor product has sections, then the degree of L has to be positive. Okay, but I won't say more about that. You can just believe that there exist curves with such bundles. And so if we take that for E, what does that imply? Well, then that implies that on X, this class of any effective curve has to be of the form M psi tensor, plus df, where D is strictly positive. That's what having a P of a stable bundle buys us. So yeah. But we also know that just even more generally, we also know this M has to be greater than or equal to 0, say by intersecting with a fiber and seeing that if you have some effective class, it's going to intersect with a fiber to be non-negative, and that's what this M is. So this tells us then that the effective cone has to be the first quadrant, basically. I'll just draw a picture. If we're in the psi F plane, then this says that our effective cone has to be exactly this region. In this case where our E is a stable bundle. Okay, so that was our first fact. But now that we know these effectives, we can also right. So we can also check what's the intersection of psi with E. So then that has to be, by our intersection pairing, that has to be D, which is greater than 0. So this implies that psi is greater than 0 on NEX. So this gives an example of a divisor that intersects strictly positively on NE of X, because we just said if E is effective, then it has to have a strictly positive D coefficient. But psi squared is 0. So psi is not ample. This tells us that psi is strictly positive on the effective cone. I guess effective cone minus 0, again, for the same reason. It's strictly positive on any non-zero effective curve, but it's not ample because psi squared is actually just 0. So this tells us that kind of you need the L squared greater than 0 condition in Nakai-Morshizon. And it also tells us that you need the full NE bar of X in Kleiman's criteria. So this is another reason why I really have to work with any bar, even though it's more complicated. We can't test things like ampleness on just any. And this example also tells us that NE is not closed, even though here everything's rational. So we already saw this example where NE wasn't closed because you have rays with strictly real slopes. But here, everything's rational. We just have this first quadrant, but still NE isn't closed. And that's again because if we look at this psi, this is an enclosure, but it can't be effective because sections of OX of M are the same as sections of sim M with no line bundle, so it's like tensoring with a trivial line bundle, and these are 0 by our stability assumption. Or really, I guess I should say, because this is psi is just a numerical equivalence class, here I should say that really these are sections of sim M of E, tensor some L, where the degree of L is 0. And that's 0 by stability because the degree of L is 0. Okay. So that gives us an example where everything's rational, but we still need to take the closure, and it's actually not closed. Questions? Okay. So now that we see some of the pathologies that can happen, let's move on to the part of this cone that is quite well behaved, and we'll see this when we study these surfaces whose canonical bundle is non-F. Okay, so here's our strategy now. The way we proved Castelnuovo's theorem is we had this curve we wanted to contract, and we produced a Neff line bundle, and then checked that that Neff line bundle was 0 only on this curve and no other curves, and that that line bundle was semi-ample, so it actually produced a morphism that contracted that curve. To study more generally these surfaces where K is not Neff, we're going to do the same thing. We're going to look at our cone of curves, which we just saw can be something complicated. And because K is not Neff, if we look at where K is 0, and then let's say over here we have where K is less than 0, we get something like this, where we have effective curves on which K is less than 0. That's our assumption. And what we're going to do to understand these, well, we're going to start with some ample A, and our ample is going to live over here. So here's the hyperplane where A equals 0. So kind of this region is where A is greater than 0 because A is ample, so it has to be strictly positive on any effective curve. And then we're going to understand the curves on the boundary of any bar x by moving this A closer and closer to any bar. So more precisely, we're going to consider line bundles of the form, or divisor classes of the form TKX plus A for T greater than 0. And so you should think kind of these LTs are going to start approaching as we increase T. These hyperplanes LT equals 0 will start approaching any bar, and eventually we'll hit something exactly on the boundary. So eventually we'll hit some T where this hyperplane, let me call it R, we'll hit some R where this hyperplane is actually tangent to the effective cone. Or not tangent, well, maybe not tangent doesn't make sense, but where it touches, or just touches the effective cone. Okay, and so what we want to do then to study the geometry of X, or what the curves look like on this ray that this L hit the effective cone on, we want to we want to say that this class is represented by an actual semi-ample line bundle, and then study the morphism induced by this line bundle. So to do that, we need to know a few things. So let's define this R, which we can call the Neff threshold, is the supremum over all t, such that t kx plus a is Neff. And that's exactly what it means to say that we've increased t until we hit the numerically effective cone, because now that we're touching it, we have something where L is 0, so it's no longer ample, but the cone is still on the non-negative side, so it's still at least Neff. So the first very important theorem, which you can prove for surfaces kind of by hand if you really just get your hands dirty, but we're going to prove more generally, so I'll move that to later in the course when we do it in higher dimensions, is the rationality theorem, which is that R is a rational number. So what this tells us in particular is that it makes sense to take some large enough multiple of LT to get an actual line bundle. So we have a hope of carrying out our strategy of understanding the geometry of X by producing a linear series. Our linear series will be the linear series corresponding to some large multiple of LR, which is actually a line bundle. That's the first really important theorem. And like I said, we'll prove this in higher dimensions, so I won't do the special case of surfaces now. And then the next theorem, which says that this MLR really does give us a linear series we can understand, is the base point free theorem. Here, I'll state it in this setting, but we're going to prove a much more general version later, which is that if A is ample and A plus RKX is Neff, let's call this L, is Neff for R rational, then L is semi-ample. I.e., the linear series associated to some large enough multiple of L is a morphism. So I'll add here large plus divisible to clear out the denominators in A plus RK. Okay, so those are the two theorems that are going to let us analyze the situation where the canonical bundle is not Neff. And now our strategy is that once we have this, then we can look at this linear series. But now we know when we have a base point free linear series, we know exactly which curves phi contracts. It contracts exactly those curves where L dot C are 0. So if we look back at our picture, these curves where L dot C are 0, they're going to span the ray or collection of rays where this LR, this L on the Neff threshold, has touched the numerically effective cone. So if we call this R, let's call R the ray on our numerically effective cone, or sorry, on our effective cone, where LR equals 0 intersects it, then this linear series, once we know it exists, contracts exactly those curves whose class is in this ray. Or maybe collection of rays in general, but here, kind of, if we pick a generic enough to do this process, then this ray, this will actually be a single ray rather than some union of rays. So okay, but now you might wonder, kind of, if this rationality theorem is true, you can't possibly have the picture that I drew here. Because if we know that we always need to only have rational slope to kind of touch the boundary of the effective cone on the k negative side, then it can't actually be round. Because if it was round, then we can move things around to get something. So that's at least some intuition, and really this becomes the cone theorem, which we'll also prove later in higher dimensions. So for now, I'll just illustrate it. So as a result of these rationality and base point freeness theorems, we actually get that the k negative side of the cone of curves has a really nice structure. So I'll draw it as a picture. So here's our k equals 0 hyperplane. And on the positive side, we don't know anything. Could be whatever. But on this negative side, it turns out that it has to be some kind of rational polyhedral cone. So it has these flat faces with rational slopes that meet at rays. These are called, these rays where these faces meet will be called extremal rays. So that means, so just a general definition, R is extremal. Essentially, if it's on the boundary, but more formally, what that means is if whenever V plus W is in R, then that implies that both V and W are in R. That's what it means for it to be extremal, where V and W start off in our cone. So an extremal ray of our cone is some ray where anytime you have two vectors in the cone that add up to land on the ray, then they actually have to start off in the ray. And this k negative side of this cone, so it has these extremal rays, it has these faces with rational slopes, and it's rational polyhedral. And I'll say it as locally finite. So there might be infinitely many faces, but the only way that you can have these infinitely many faces is if they accumulate toward the k equals 0 hyperplane. Anytime you pick some open subset that's strictly on the k less than 0 piece, then within that open subset, you just get a finite rational polyhedral piece of your cone. So the only way you can have infinitely many extremal rays is if they accumulate toward k equals 0. So this is the big structure theorem about the cone of curves. That will be the focus of basically the first half of the class. And then the contraction part is the analog of the base point freeness theorem, which says that there exists a contraction for each of these extremal rays. We'll see that there exists a morphism. And the way we'll see it is by producing the linear series, just like we described above. So there exists a morphism phi r from x to z such that phi r of a curve is contracted to a point if and only if the class of this curve lies in this ray. We start with our X, whose canonical bundle is not an F. Pick some ample generically and run this strategy. So we have L is RKX plus A, where R is the F threshold. And now because we picked it generically, we can assume that L equals 0 intersect our cone of curves is a single ray, and it's extremal. And now let phi be our morphism, which we get by the basepoint free theorem. Then we have this morphism. We know that it contracts a curve if and only if it's in this ray R. And now we're going to use that to classify the possibilities for phi based on the dimension of Z. So that's where we'll go at the beginning of next class. And that's exactly where our classification theorem will fall out of. We'll see that either phi is the blowdown in Castelnuovo's theorem, so this extremal ray comes from a -1 curve, or phi is a P1 bundle, so then we're in the ruled case, or Z is a point, in which case that'll force X to be Fano, so then we're in our third case. And so in particular, if we also know that X is minimal, that tells us that Z has to either be 1 or 0 dimensional, so we get either a P1 bundle or a Fano. So that's where we're going.